Hi everyone, welcome to lecture number 8. Today we're going to be continuing on our Learning to See series. It's just a pre-recorded lecture today. We can't do it live unfortunately, but we'll be back live next Tuesday. And just a reminder to go ahead and get started on your programming challenge, right? So that's going to be due pretty soon. A lot of the tricks that you'll need on the programming challenge, you won't really get until it's getting pretty close. But what I've done is if you go to the programming challenge notebook here on the in the repo, I've given you some advice, right? So we're going to do this whole thing in this module and learn about decision trees and learn about machine learning. And the outcome is going to be rules that we'll kind of work our way towards. And I've kind of given you some of those rules right here. And what I need you to do in the programming challenge is to take those rules that help us find fingers, and you put those together to count the number of fingers in an image. So the reason I point this out to you is that it's going to take us a little while as we go through the series to get all the way to decision trees, because we're going to really build it from first principles. So it's better if you can go ahead and get started and start experimenting with the programming challenge. The sooner you can do that, the better. Submitting the night before is not a great idea. The server is going to slow down. It will slow things down. It stresses out our TAs. So do try to get ahead. Okay, so that said, let's get into our lecture for today. And we left off last time with a really fun challenge or a fun exercise to think about. So just to remind you where we are. So last time we explored a few different strategies for finding fingers in images. And the whole goal here was to find the pixels that corresponded to fingers. We started with a couple simple approaches where we would make some rules that we thought described what the little neighborhoods of fingers would look like. So we tried searching for patterns like this in our images. We took binary images, so it was just ones and zeros. We searched for patterns like this. Neither of these approaches did too well. So last time we learned about recall, we learned about precision. And using those techniques to measure our performance, we didn't do so great. Remember that our recall was, our accuracy was pretty good, but remember that there's a reason for that. It wasn't for a great reason. The reason our accuracy was pretty good is because our data set is imbalanced, so it's actually very easy to achieve high accuracy. So next time someone is telling you how awesome their machine learning model is, ask them what their precision and recall is, not just their accuracy, because that's very important. Okay. So we left off with a little bit of a cliffhanger, I think, which is that we tried our very first machine learning model. And that model basically consisted of doing what we could basically kind of call memorization. So let me show you what I mean. So let me go back to that lecture just real quick for a second. So I'll go back to the second notebook. Okay. So what we left off with here is we said, okay, let's extract all of the patterns in our images. Here's our images again. We extracted all of the pixels that correspond to fingers. And for each of those little pixels, I found the neighborhood. I found the 9x9 grid around that pixel. And I said, okay, let's take those examples. Let's take all the unique examples. It turned out there were 413 unique examples. Here they are. And our very first machine learning algorithm was actually really, really simple. We just said, okay, let me zoom in a little bit. We said, okay, let's just let these be our rules. So going forward, if we find any matches to these patterns, then we're going to call it a finger. And that's going to be our first machine learning algorithm. Okay, so we tried that, and we measured its performance, and it turned out that it did really, really well. So it had an accuracy of 100%, a recall of 100%, and a precision of 97%. So we're done, right? We got it. We figured it out. We win. So not quite. I've kind of tricked you, but only for a good reason, I promise. I've tried to show you a way that maybe seems logical to kind of show you one of the biggest challenges and one of the biggest things to look out for in machine learning. So what have we missed, right? What have we gotten wrong? What have we overlooked in developing our first machine learning algorithm? So really, in a nutshell, I would like to just say it like this. I would like to say, hey, memorization is not the same thing as learning. And what we've done, really, with those 413 examples is we've memorized a bunch of examples from our data set, and we've looked for exactly the same thing in our test data set. It turns out this does not work well. And it seems like it might, right? But we're going to get into why. We're going to get into some math, and really we're going to get to the core of why machine learning works. This lecture, this series is a little bit more theoretical. The rest of the class will be more practical, but I think it is helpful to cover some of the theory. There's a really great quote. It's actually from one of the authors of one of the books that we're going to reference in this module, a great book called Learning from Data. And there's a great quote in that book, and it's that there's nothing as practical as a good theory, right? So practice is certainly very important, but a good theory really will help inform and drive your practice. So that's why we're spending some time on theories. So in the video series, I make a big point about this, and I'm like, I use this quote from Richard Feynman, and I say, hey, memorization is not learning, and I mean it kind of on two levels. I mean it kind of on a philosophical level, which I do believe, but that's the philosophy, right? This class is not about philosophy. This class is about computer vision. But it does, I think, inform how you think about these things, right? So I like to spend a little time talking about it. I think this is really true in life, especially as a student. This is relevant to think about. Memorizing is not learning, right? It's true for machine learning algorithms, and it's true for you as well. So hopefully we've set up this class in a way that you're not encouraged to memorize. There's only a few things I'd really like you to just know. But really, learning is different. Learning is not about just memorizing facts. Okay, so and one other misconception I hear that you'll see sometimes is people talk about machine learning. And when machine learning algorithms get something wrong, sometimes people say, oh, the algorithm hasn't seen that example before. But that's not really how machine learning works. And we're going to get into that in more detail. That's another complication. These algorithms are not memorizing data. They're doing something very, very different. They're learning, we hope. So let's get into that in more detail. What do we mean by learning? How do we measure learning? What is learning? And we're not going to answer that whole question, right? But let me give you a good way to look at it, and a way to look at it that we use all the time in machine learning. So, if a professor or a teacher or someone like myself wants to measure or understand how well you've learned something, right? I'm not going to give you a test that has the same problems that I gave you on a practice test or in your homework. They're going to be different, right? So just like I'm doing that to prevent you from memorizing, right? For our machine learning model, we can do the same thing. We can have our model, and we can test it on examples that we did not train on, right? So this is the idea of a test set. We're going to have a test set, and this is really, really important. So test sets really are critical in machine learning. You should really always have a test set to know how you're doing, and we'll see why that's so important soon. So with this first little block of code here, I am going to evaluate the performance of our machine learning model on a test set. So let's do it. So last time we used these three examples, example 0, 1, and 2 in our data set to learn our classifier, to learn those patterns to look for. And now let's test it on the next two examples. So we'll look at images 3 and 4, and we'll evaluate the performance on those examples. So let's do it. I'll run this cell. So here are the two examples. So we haven't seen these examples before, and let's see how our model does, right? How does our memorized 413 rules, how do they do here? So let's do it. Let's run these through our algorithm. Let's have a look. So this is the result. This is the result of our model. And remember, just a minute ago, we were celebrating because our model did really well, right? We got this kind of performance, right? We got all the fingers right, just a few false positives, amazing, right? But now that we've switched to an actual test set, performance is not great, right? So maybe start thinking about why. And while you're doing that, while you're thinking about why, I want to ask you a question. So this will just kind of probe your understanding from last lecture a little bit. Last lecture, we introduced two very important concepts, recall and precision. And now, I would like to kind of test your understanding of those. And I would like you to estimate, just roughly, I want you to estimate, what is the precision and what is the recall of our rules, of our first machine learning model. So here's the images again, and you can see that we're missing quite a lot of fingers, right? And if you're missing finger pixels, that should decrease your recall rate. Remember, recall is the number of actual examples that we capture with our algorithm. Remember, precision is the number of examples that we get correct, basically. So let me rephrase that. It's a little tricky. So recall or precision is of all the predictions we make, what percent of those predictions are correct? So that's precision. So please pause the video at this point, since this one's not live. Take a second and pick your answer. And then once you have unpaused, we will pick up with the answer. So do pause your video. Okay, 3, 2, 1, pause. Okay, you're back. All right. Hopefully you actually paused and you have an answer for me. So I'm not going to tell you the answer right away. We're actually going to compute it, but hopefully you have an answer in your head for what you think the recall and the precision is of our first machine learning attempt. So now let's go ahead and measure it. So let's get our data together. We're going to actually compute the confusion matrix using some confusion matrix code here. I won't walk into exactly how it works. It's not too bad. That the inner workings of the Python code they're not terribly important in this module. Feel free to have a look at them. But in the next module or so, when we get into neural networks, then we're really going to drive deeper into Python and into PyTorch and libraries. But right now, this module is a little bit more about concepts than it is about code. So I'm not too worried about you understanding every line of code in this module. Okay, so here we are. So we computed a confusion matrix, right? And we're going to answer this question, basically, right? So to answer this question, we have computed a confusion matrix, and now I have another question for you. So please take a minute, do a little math for me, and please compute the precision and recall of our model using this confusion matrix. So again, please pause for a second, and then we will go through the answer. So 1, 2, 3, pause. Okay, and you're back. Great. All right. It's funny, I'm kind of pausing too, but if you actually pause the video, then I don't need to pause. So I'm going to try to not pause next time at all in the video. It's going to be kind of awkward. Okay. So let's do it. Right. So remember recall, and what did I ask for first? Yeah, recall. Okay. So recall is the number of actual fingers that we capture. So the recall is going to be equal to 45 divided by 45 plus the remaining examples of actual fingers that we did not capture. So that number is 351. Those are the false negatives. And that should be our recall. Let's print it out real quick. Let's see what we get for recall. Cool. So we get around 11% recall. So not great. So I think the answer is going to be C. But let's go ahead and compute our precision. Here we go. So precision is going to be equal to 45, the number we got correct, divided by 45 plus. Remember, precision is the percent of predictions that we make that are correct, the percent of finger predictions or percent of positive condition predictions. So we predicted 45 plus 25 fingers. So 45 plus 25 in the denominator gives us a precision of 64.2. So about 64%. So the answer is C. Great. And if we scroll back here, the answer here is going to be, I believe it is C. And this one's not a big deal. We were kind of having you eyeball this, but yeah, the recall is less than 25%. Hopefully you can kind of see that. We're missing most fingers. And the precision is over 50, but not much over 50. Okay, great. So all that to say, kind of back to the main idea here, here's our big table. All that to say that if we expand how we look at our results, right? So remember last time we just were kind of looking over here. We were just looking at performance on our training set. And if we expand our results and look at a test set, we get a really different story, right? So remember on our training set, we had an accuracy of 100, a recall of 100, a precision of 97. That's incredible. Go over here though to our test set, and it's a very different story, right? So our recall is 11%, terrible, and our precision is 64%. So really, really bad, right? So, so far, hopefully you've picked up on the idea that learning from data is not the same as memorizing data. And the way you know if you're actually learning, or one way to measure if you're learning, is to measure your performance on a test set and see how you do. So that is an industry best practice. We're going to do that all the time. So test sets are here to stay. So don't forget about your test set. Okay, so that's great. What I want to do is I want to address a way that we might fix this. So a very common kind of response, especially now that deep learning is in vogue, is, hey, let's just add more data, right? Sure, it didn't do well, but maybe it hasn't seen enough fingers, right? Maybe there's just more fingers that we need to see, right? That's reasonable. So let's explore that hypothesis and let's see, are there just more fingers that we need to see? So remember that our original data set had actually 42 images of hands, so a bunch of images of hands. So let's use more of them and let's see if we can do better with more data. So let's try it. Let's see if more data fixes the problem. So now I'm going to add a bunch of training data, more examples. We're going to end up with, here they are, so I'll show you. So we're going to now use 30 images of fingers. Before we were using just 3, and now we're at 30. So we've increased our data by tenfold. So maybe take a guess, right? So if the world was a nice, friendly place and we had a really good strategy, maybe increasing our amount of data by 10. This is 10 times the amount of data. Maybe that would increase our performance by 10. Maybe that'd be nice, right? So let's see. Think about your hypothesis. Is performance going to go up, go down, 10 times better, twice as good? What's going to happen, right? Okay. So now, remember before we had 413 unique examples of fingers. Now we actually have 3,035. So that's a lot, right? We have 3,035 unique examples of what a little neighborhood around a finger pixel could look like. So that seems like it could be a pretty useful thing, right? Hopefully, if we look for those patterns in some new data and some test data, hopefully we'll do pretty well, right? I mean, come on, that seems reasonable. So let's have a look. So here we go. So here is our performance on our test set. So this is going to take a second, I guess. Yep, cool. All right, how does it look? What do you guys think? How have we done? Good or bad? I'll give you my opinion in a second, but let's measure it, right? We're here where we can be scientists and measure these things. So here's the confusion matrix. And what I really want to get into, of course, is the precision and the recall. Here's the confusion matrix we get out. Here's the precision and recall. What I really want to show you is this. So here we are back at our big table, and we have another row now, and this row is very similar. But now we are looking at 30 images in our training set. That results in, I think I said 3,000 examples earlier. It's actually 2160, I think, after you remove the duplicates, I believe. So you end up with around 2,000 examples of finger pixels, which sounds like a lot. Again, on the training set, we do very well. Notice that our precision drops down a little bit. That might be worth thinking about. Why did our precision drop? But the real thing, of course, is the test set over here. How did we do on the test set? And as you can see, our performance is real bad. So our recall did go up, so it doubled, but our precision went down, so we have more false positives. So, throwing 10 times the amount of data at the problem did nothing, which should tell you that we have a crappy strategy for learning from data. Doesn't matter how much data you have like this, if you're just memorizing, you're not going to do well. So hopefully that makes sense. Hopefully that kind of has hit home a little bit. Really that is, this is a big key concept. So, if you're going for a walk or have a little time to ponder the wonders of the universe and why things are the way they are, this is a cool thing to ponder. Why is it that we can't just memorize these examples? Why isn't learning memorizing, right? Why are these not the same thing? So, and really, if you start to think about why this doesn't work, that can lead you to hopefully a better machine learning strategy. So it's not just all about philosophizing, even though that's fun. If we really have a careful look at what's gone wrong here, it will lead us to a better strategy. So let's get into that. So the question to ask then is why? Why did our model perform so poorly? And there's a few ways to look at this, but there's one way that I like. So there's a way I like to think about this. So I like to think about the examples that we've seen. So, we had, in this first case, 400 examples of fingers. I think 495 here. This table might be slightly different than my code. I think it's because when I made the YouTube series, I used a slightly different training set than I did in these lectures. So if these numbers are a little different, don't worry about it too much. The same principles apply. But either way, oh no, I'm sorry. It's 400. No, it's right. This is 413 examples. So this number does match. There's 495 pixels, but if you take the unique ones and remove the duplicates, there's 413 unique examples. So anyway, we took those examples and used that as our rule. Okay. What I'd like to think about though is the examples that we've seen, these 400 examples, or in this case, these 2,000 examples. What percent of all possible examples does that represent? if there's a universe out there of all the different images, all the different little grids of 9x9 grids of ones and zeros, if there is a universe out there of all the different examples, how many have we seen? How much of that universe have we been exposed to, right? That's what I want to think about. So this is really what I want us to start thinking about. How big is this universe? And actually, we can measure this very rigorously. It's not too hard. It's just a little bit of math. So as you might have guessed, I'm going to ask you to do it. So my question to you, remember that the examples in our data set are 9x9 grids of ones and zeros. And some of them represent fingers and some don't. So what I'd like you to do is take a minute and think about how many of these grids exist, right? How many unique grids of ones and zeros exist? So please pause. Okay, welcome back. All right, so hopefully you have your answer. How many unique grids exist? So let's go through, walk through this. So here's how I'd like you to think about it, or here's how I think about it, I should say. So for every individual pixel, there are how many possible values? There's 2, right? There's 2 possible values for each grid. So if you had 2 grids, for example, there would be 4 possible values. It's 2 times 2. So you multiply each time you add a pixel. If you had 3 pixels, it'd be 2 times 2 times 2. There's 8 total options. So here it's going to be 2 to the power of 81. I think Python's going to blow up, so this will be fun. I'm not sure, but I think this number is bigger than Python can deal with. Maybe I'm wrong, though. Let's find out. It's integer. I think the default format is in a 64-bit integer. I'm not sure. All right, here we go. Oh, no, I did it. Okay, I'm wrong. Sorry. That's nice. How big can we go? Oh, never mind. How is it doing this? All right, I could talk about this for a while. It's not NumPy, I guess. Okay. Like if I do a type of this, all right, this is a brief diversion. Feel free to skip this 60 seconds of the of the video if you want to. So it's just an int. Am I forgetting how big a 64-bit integer can be? Holy crap, that's really interesting. Let me do one more thing just for fun. Bear with me. Ready? Okay. I'm just curious if I make this a np.array of 2 like that. Okay, cool. And then I do this. Yeah, okay, there we go. Okay, that makes more sense. All right. Yes, okay, cool. Let me just share what I did really quickly. So I was really surprised that we didn't have what's called overflow here. I thought that Python would not be able to support numbers that big. I didn't know what kind of data type it was using. This is relevant for computer vision. We talk about data types. Remember, most images are stored as 8-bit unsigned integers. Here, when I just made this this array, I'll just call it this array A. If I do a.dtype, and I promise I will answer the question in 1 second, but just to show you what I'm thinking here. If I do a.dtype, like this, cool. So this is a 64-bit integer. A 64-bit int, we should be able to roughly express numbers as big as 2 to the 63rd power, I believe, because we have to include negatives as well. So this should be like the biggest number we can represent in using this data type. So what I'm getting at here is that as we raise a to higher and higher powers, like things are going to be fine until we get bigger than that number, and then we're going to get overflow is what's going to happen. So yeah, that was overflow, but I kind of want to prove it to myself. Like if I do like 30, for example, okay, 30th power is fine, 40th power is fine, yeah. As soon as we get bigger than around this number, it should overflow. So that's pretty interesting. If I go to 70, yeah, there we go, cool. Okay, anyway, so apparently in native Python, which is not NumPy, so this is not a NumPy number, this is a Python integer, it can support actually bigger than 60, it must just use bigger data types. So that's pretty cool. I had no idea. That's very cool. I learned something about Python today. Now anyway, back to our problem, right? So the answer is 2 to the 81st power, which is this. To figure out this is 10 to what power, I believe we can do the log base 10. Let's see, is that built in? No. np.log10? Let's see. I think np.log is natural logarithm. Yeah. I believe. Yeah, it's natural logarithm. Yeah, okay. Oh, there's a log 10. Okay, All right. So we're almost there. Hang in there with me. So if I do np.log10 of 2 to the 81st. Oh, you know what though? We're about to have a problem because NumPy can't express stuff that big. That's right. All right. So we're gonna approximate here. And also just one other thing you can do. So I'm hacking around on Python here. You could just go to Google if you wanted to. And if you do 2 to the 81st power, it will tell you that it is 2.4 times 10 to the 24th, which is approximately this answer. It's a septillion or something. It's really, really big. That's what we're getting at here. So I could keep working on the Python stuff. I'll let it go for now, but just know that this is 2.4 followed by 24 zeros. We could also just count the zeros instead of doing the logarithm thing if you wanted to. If you counted the number of digits here, you should see about 24 digits. So all that to say, with that fun diversion about data types, all that to say that there's a lot of these, right? The universe of possible 9x9 grids is real big, right? It's huge. So maybe I'm going to throw one more question at you, but in the meantime, just start thinking about what that means, right? What does it mean that there are 2.4 septillion examples and we've seen like 400, right? Why might that be important? Why could that mean, what could that have to do with our struggling to learn, right? Okay, and then just one more fun thing for you. This is not going to be on a quiz or anything, but I think it's kind of cool to think about. So, you know, a lot of the video you watch, you may be watching this video right now in full HD, which is 1920 by 1080. It's not quite as fancy as 4K, but it's pretty high resolution. What's fun to think about is how many unique full HD video frames exist. So in the whole universe of all the possible frames you could ever make, how many are there, right? How many unique frames exist? And it's actually really the same exact kind of math. It's a little different now because we're going to be using 8-bit, and a lot of video content uses 8-bit color. Now it might get compressed. Most video will be compressed, which kind of changes the number of possible frames, but we'll ignore that for now. We'll assume raw video. So that means for every color channel, there are 2 to the power of 8. So there are, sorry, I got cut off for a second. Okay, so that means that for every pixel, there are 2 to the 8th power, or 256 possible values that pixel could take, intensity values. And there are 3 pixels per, or 3 color channels per pixel, excuse me. So this is the number of values you could have per pixel, because 3 color channels, and each pixel can take on 256 different intensity values. And now we know that there are a bunch, a whole bunch of pixels, right? How many are there? There are 1920, oops, excuse me, times 1920 times 1080, that's the resolution, cool. And this is to that power, right? So this is gonna get tremendous. Man, is Python gonna even be able to handle this? I think Google can do it, but you're gonna get a massive, massive number here, which is kind of the point we're driving at. Let's see how Google feels about this. I'm not sure if I can type it with the same syntax. No, not quite. I have to use carets, I think. We'll see if Google can handle it. No, man. Okay, interesting. All right. So we're gonna get a huge number here. There's a couple of shortcuts we could use to figure it out, but fun to think about, right? So I don't remember which exact answer it is, but if you figure it out, let me know. I'm sure there's a way to do it. I might have used Wolfram Alpha when I did this last time. Python will load this eventually, but the point here really is that there's just a huge number of possible images in the world, and no matter how big your training set is, you're only ever going to see a tiny, tiny portion, and that really impacts how we do machine learning. So let me interrupt my kernel because my MacBook's going to catch on fire because I've asked it to compute such a big number. Cool. Okay, so what I really wanted to show you is this, though. So, you know, as far as the number of unique examples that we have, so here I'm counting up the number of finger and non-finger examples. So if I take those two together, we end up with around 20,000 examples in our data set, which sounds like a lot. But what's fun to think about is, you know, what percent of the overall universe of examples does that represent? And it turns out that it's 0.000000000000000000085. So it's like nothing. So Our little data set, and really any data set you're going to collect as a human, any data set of images that you collect is a vanishingly small percentage of the possible data out there. So that really, I think, has an impact, and it will have an impact on how we should think about learning. And I think it hopefully gives us some reasoning to use to think about why memorization failed. If there really are that many examples, and you've only seen this percent of them, then of course memorizing fails, because you've only seen such a tiny percent of the whole world, right? This is why memorization in this sense doesn't work, or it's one reason, one way to think about it not working. So these are the questions I want us to think about. So the questions now are, so if that's all true, Stephen, then how can we learn rules that will actually generalize, right? So what can we do, right? How can we make sure that our rules, and generalize is a term that I've just brought into our class, and it's a very, very important word. And really it just means that the results you see on the training set generalize or continue to work on the test set. And question number 2 is, how can we actually learn anything if we've only seen a tiny portion of all the examples, right? How can we learn? So those are the questions I want you to think about. And to help us think about those, we are going to simplify our problem. So we are going to go down to a toy problem to get us to really think about how we learn rules and some of the math that goes into this. So the toy problem is this. So instead of doing 9x9 grids, we are going to do 2x2 grids. So we're going to break it down even smaller. And it's going to be a very, very similar question. Excuse me, I hit my space bar. Okay, it's a very similar question. So now I've made our data smaller, right? So here's a little training set. Here are 5 training examples, 1, 2, 3, 4, 5. And for these training examples, I would like you to think of a rule. So these 3 examples are positive. So these are kind of like the fingers in our real data set. And these 2 examples are negative. These are like the non-fingers in our data set. And what I'd like you to do is to take a second and please think of a rule. Think of some rule that you see that you could use, a rule that you would learn from this data set to make a decision about which class this image should belong to. So please pause, take a second, and pick back up, and we will talk about the answer. Okay, welcome back. All right, so hopefully you paused, and you have a rule, and you've decided which class this responds to. So normally, I'm a little bummed that we're not doing this one in person, because it's fun to make this into a poll. I think last year in the class, like half of people said this should be positive, and like half people said this should be negative. So who's right? Is it positive or negative? So the answer is you're both right. So it's both positive and negative. And let's talk about why. Let's talk about some of the rules that you might have come up with. So normally in class, I'd ask you what your rule was. So hopefully you thought of a cool rule. Those of you who said positive, your rule might have been something like, hey, if the upper left pixel is positive, if it has a colored in or a value of 1, right, a colored in positive value, and it's not empty, if the upper left pixel, upper left value is filled in, then it must be positive. So these 3 all have an upper left pixel that's filled in, and this one also does, so it must be positive, right? Okay, done. Now, those of you who said negative, your rule might have been something like, hey, let's add up the number of pixels. So this has 2, this has 2, this has 3, this has 1, this has 1. Okay, so things that belong to the negative class have 1 pixel. They have 1 positive, 1 filled in value. And that's a valid rule. We can express that in mathematics. We can write it in code, no problem. And that gives you the exact opposite answer, right? So who's right? Which rule's better? How do we decide? So I'm not going to answer the question because it's a little bit of the whole point of the question is to get you thinking here. But I want to give you a harder question now. And this question really kind of gets into the root of what's going on with machine learning and how we get it to actually work. So you guys as a class hopefully just found at least 2 rules that fit the data. Like we said, one of the rules might have been that anything with a positive value up here belongs to the positive class, and anything with a value of 1 or a positive value here, or excuse me, or anything with with only one value filled in belongs to the negative class. So those are two rules that both perfectly work. So here's my question to you. Are there any more rules? So are there other rules that perfectly fit this data? Sorry about that. And if there are other rules, if there's more than two, how many are there? Are there infinity? Are there 16? How many are there? So we're having to go a little faster in this lecture. So we'll probably start the next one real quick. We'll get into the next lecture a little bit. But I kind of recommend, you can watch this however you want, but now is a really good time to pause. And I'm going to keep going and go on to the next lecture a little bit to kind of get us going, because we only have one lecture left in this module, because we're going to end with a guest lecture. But this is worth thinking about. It's worth thinking about, I promise. And if you want to see the answer, you can watch parts 6 and 7 of the Learning to See series, or you can keep watching this lecture. But it's worth thinking about. How many rules fit our data? Okay. So let's go ahead and hop to a little bit of the next lecture. And hopefully you can see my screen okay. I'm going to keep it just like this, so I know that I'm not in presentation mode, but I think that's okay. My monitor makes it difficult to do that. Okay. So by now, I'm kind of hoping you've seen 6 and 7. Because now we're going to get deep into the stuff we covered in 6 and 7. So let's get into that. Okay, cool. All right, so this was the question we left off with. How many rules exactly fit our data? And I would like you to come away with from this with an understanding of how we're thinking about this, or how to think about this, problems like this. So let's get into some of the rules we're going to use, or how we're going to set up our rules. So first of all, let's set up a little bit of math. So let's give our 4 variables names. We'll call them x1, x2, x3, and x4. So we can express each example as a vector of length 4. And let's say that our data comes from the Boolean domain, which means that x can only have a value of 0 or 1. So just like we've been talking about, the data can only have values of 0 and 1. Okay. Now we're going to use some logical connectives, and I think a lot of folks in the class have seen these, but just in case if you haven't, we're going to use what's called an and, an or, and a not. So it's pretty simple how these things work. It's not too complicated. So logical connectives, they're kind of like pluses or minuses in algebra, but these are for Boolean logic. So an and returns a result of true if it's 2 arguments, if it's 2 values that you use that you and together. If they're both true, then the output is true. If they're both false, the output is false. And if one is true, then the output is false. That's what and does. Or does kind of what it sounds like. So if A or B, or if x1 or x2 is true, then the outcome is true. And if neither are true, then the output is false. It's 0. And then not does what it sounds like. Not 0 is 1, not 1 is 0. Okay. So now let's get rigorous, right? Let's really get into it. So and this is cool. We're going to completely discuss how to answer this question, and how to hopefully how to think about how to make rules to describe examples like what we've seen. Okay, so what I have on the screen is I've laid out all the examples. So these are all the different combinations of examples you could see. We are kind of lucky with this data set, and I've chosen it this way, that there are not that many examples. So remember the whole universe of examples of 9 by 9 grids. It was 2 to the 81st power, which is big. Here we have 2 by 2 grids. So how many examples are there? There's only 16. And here they all are, right? Here's our 16 examples. Here's every example. Remember in our question that I asked you here, I showed you 5 examples, right? Here's 5 examples. And these 5 are 5 of the 16 possible, right? So, and here are all 16, and I've colored the same examples. So here's that one that has a lower left value, right? So that was yellow, it was negative. Here it is. So I've colored all the 5 examples that are in our training set. So in this toy example, the whole universe has 16 examples, and our training set has 5, and our test set could have up to the remaining 11, right? It could have the remaining 11 examples. And what I'm showing you here is I'm saying, okay, here's our input, And there's a really good book called Learning from Data that we're going to, we won't get into it too much, but I think what I can show you actually, maybe just real quick. If you're interested in this stuff, yes, please have a look at these books. They're really, really excellent. Great reads if you're bored during pandemic. What I was just referencing, a lot of the ideas that I'll show you here are laid out also in this Learning from Data book. It's a really, really excellent book. And then there's also a really great book. So this one's a little more technical, but this book called Probably Approximately Correct. This is much more readable. It's by Leslie Valiant. He's a Turing Award winner, winning computer scientist. Really, really smart guy. And this book is a little bit more approachable, a little bit more readable, a little bit less math, but they're both excellent. So anyway, back to here, right? Okay, cool. And really the reason I emphasized this book, the Learning from Data book, this idea I'm about to share with you really comes from that book. So let me share the idea with you. So the idea is this. The idea is there's some function out there in the world that we're trying to learn. So here I've called it f. So there's some function f that we're trying to learn. And that's our goal in machine learning, is to learn some function, right? Some function of inputs that produces some output. Now we don't know f. We don't know what it is. We really can't know f because all we have is data. But we do know what f is, in this case, in 5 specific cases. So for these 5 cases, we know exactly what the value of f is. That's our training set. And our job as computer scientists is to approximate f, or to figure out what is a reasonable thing for f to predict for the remaining examples for the test set, right? So we don't know what f is, but we do know what its value is in 5 locations. G, so this next column, G, G1 is a hypothesis, right? So this is a guess. This is one function that may be the underlying function. Maybe G1 is the right answer, right? So G1 is one possible answer that we'll talk through. Here's the formula for G1. G1 is the rule that many of you may have thought of when you first saw this challenge. So if I go back to here, those of you who said, okay, if the upper left pixel has a value of 1, then it must be positive. That rule written in math is just this. It's g of bold x here, which is the vector, is equal to the value of x1. Recall that x1 is the upper left corner. So this rule in math, it just says, hey, if the upper left corner, if the first x value is 1, the output is 1, it's true. So whenever that upper left pixel is positive, or is 1, the outcome is true or positive. What I've done here, as you can see, is I've sorted the examples. So everything on the left are all the examples that have a positive value in the upper left-hand corner. And over here, these are the examples that have a negative value or an empty value or a 0 in the upper left-hand corner. Okay, hopefully that makes sense. This is called a truth table, generally. On this truth table over here, you can see that every time x1 is 0, the outcome is negative, false. And every time x1 is 1, the outcome is positive. So this is one rule. So there it is. Okay. And remember that the whole thing we're doing here is I'm trying to talk you through this, or to help you think through, or to think together through this question, which is how many rules perfectly fit our data. Okay. So we did that. Now I want to show you another rule. So here's another rule. This is the rule that some of you may have thought of, and it's the rule that says, hey, if there are 1 or more filled in pixels with a value of 1, then I'm going to call it the example positive. And if there are 1 or less, excuse me, I said that wrong. If there are 2 or more filled in pixels, we're going to call this positive. And if there are 1 or less pixels, we're going to call it negative. So we can write this in math. Here's one way to write it. This I stands for the indicator function. So if this is true, then the outcome is true. And I'm just saying sum up all the x values, add them together, and if they're greater than 1, then the outcome is positive. So in our truth table, you can see that here, 0 plus 0 plus 0 plus 0 is 0, so the outcome is negative because it's less than 1. Here, 0 plus 0 plus 1 plus 1 is 2, so the outcome is 2, which is greater than 1, which makes this positive. And what I really want to point out here is, for the training examples, just like we saw in when I asked you this question initially, this rule works, right? So we have negative here, and that's our ground truth label is negative, so this matches, this matches, this matches, this matches, and this matches. So both of these rules are perfect, right? They perfectly capture our training data. Okay, cool. And we've shown you that here's 2 rules that perfectly capture the training data. And hopefully you've had a chance to think, are there any more of these, right? Is there a G3, right? So let's get into it. As you may have guessed, there is a G3. And before I tell you the formula, I would like to just show you the data. So I've made a G3 here. And notice that I filled out the truth table for you, but I haven't told you the formula yet. And here it is. So for like 0, 0, 0, 0, we get negative. Notice where the positives are. So 0, 1, 0, 1 is positive. 0, 1, 1, 0 is positive. So look at where the positives are. If you'd like to pause for a second, feel free and try to think of what the formula is. I'm going to go ahead and hop to the next slide. So here it is. So the rule here is G3 is equal to x1 or x2 and x3 or x4. So the way this works is that if we do an OR operation first, right? So we take this pair, and if one or the other is true, and one or the other of this is true, then the outcome is true. And it just so happens that this rule, G3, exactly matches our training data. Look, so we have a plus here, plus, 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 minus, 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 minus. Everything is perfect, right? So here is a third rule that works. So that means that our answer is not A, right? So A is out. So it must be B, C, D, E, or F. Okay. All right. So now I would like to introduce you to another rule. So you may have guessed there's more than 3 of these. Let's get into it. And this one I'm going to try to really make a point with. So I've made a rule here, and look at the truth table with me. I've made a rule that exactly captures the positive examples. So it's negative everywhere except for this example, and this example, right? So it's positive for 1, 0, 0, 1, 1, 0, 1, 0, and 1, 1, 0, 1. Okay. Think for a second. How could you make a rule that does this? Using and or not logical connectives, how could you accomplish this? So again, feel free to pause if you'd like to. I'm going to go and go to the answer now. So here's the answer. So have a look at this formula. So I'm saying x1 and not x2 and x3 and not x4, or x1 and not x2 and not x3 and x4, or x1 and x2 and not x3 and x4. So it's kind of a mouthful. It's kind of gross, right? But what have I done? Hopefully it's making a little bit of sense. What have I done here? So look at this first rule. This first rule is only going to exactly match one example. Who's it going to match? It's going to match the example that has a 1 for the x1 position, a 0, a 1, and a 1. So it only, I'm sorry, I said that wrong. It's going to match 1, 0, 1, 0. Yeah. So it exactly matches this example. So I've made this custom little part of a rule that perfectly catches this, right? And I've ORed it. I've said, okay, if I perfectly match that, perfect. Or if I perfectly match this, great. And you notice that this is 1, 0, 0, 1, which is this pattern, right? So that's the idea here, right? Notice that I've made a rule that perfectly matches the data. And what I'd like to point out to you now is that if I can make a rule that arbitrarily matches any combination of values, right? Then I should be able to make any possible combination of truth table values just by using ands and ors. And what that means is that there are many rules we could make that exactly match our 5 examples. And instead of having us write them all down, because it would take a while, I just want to think about their truth table values. So if we're going to match our training data, then we need to have, like this row has to be fixed. We have to always predict negative or false for this row. Same for this row. And we have to always predict positive for these 3 rows. But that leaves 11 rows that could be anything, right? And I've just shown you, I hope, that we can actually write a rule that captures anything. We can write a rule that has any arbitrary combination. So another way to think about this is we kind of have 11 free variables. There's 11 things that could be anything. So to find the number of rules, actually all we have to do is just do 2 to the power of 11, because there are 11 free options. So here I've shown 26 of the options. There's more, but it's every possible combination is a possibility. So the answer then is 2 to the 11th, which is 2048. So when I asked you, a little bit earlier, I said, think of a rule. You may have thought of 1 or 2 or 3 rules, which is great. And this is going to be important because when we turn this job over to a computer can think of these rules way faster than we can. It can try many, many rules. And there are 2,048 rules that would perfectly describe this training data. So that's kind of crazy, right? That's a lot. And that's going to matter a lot in a minute. Because what's going to kind of really matter, and kind of the next concept that I really want to get to, is kind of the fundamental nature of machine learning and about this idea that machine learning is ill-posed. So that's a term you'll see in the literature and the books. And what it really means is that, hey, there are 2,048 rules that perfectly fit the training data. So how do we know which one's right, right? How do we make an argument, if we go back to this example, those of you who picked, the rule that said that the test, actually, what I really want to go back to, bear with me one second. Yeah, here. So those of you who said that this testing example is positive because the upper left-hand corner is 1, versus those of you who might have said that this example is negative because there's only one pixel or one filled-in value, one value of 1. Like, who's right? How do we know which is a better rule if we're doing machine learning? And it's even worse than that. There's not just 2 rules that disagree. There's 2,048 rules. And actually, it's kind of funny. If you let those rules vote and you say, okay, let's take them and see, let's do all the rules and let's see what they each vote for this one. It actually comes out dead even. So you'll have 1,024 saying it's positive and 1,024 saying it's negative. So that really, it's a way to think about this idea, or that's an example of this idea of machine learning being ill-posed. There is no one unique answer to these problems. We can only ever have approximations. So I think that's an important concept to grasp early in machine learning. It's only an approximate science. It will never be perfect, just kind of by definition. So another name that gets thrown around for this is the futility of bias-free learning. We'll get into what bias is in the next lecture. It has a mathematical definition that we'll get into and a nice conceptual definition. I guess we'll really talk about the conceptual definition. There are some mathematical definitions, but we won't cover those in this class. But what we're saying here is that if you don't do this thing called having a bias, which we'll get into in a little bit, you can't learn anything. So if you try to let anything be a rule, which we'll get into this in more detail, you can't learn. So this idea is called the futility of bias-free learning, and it's going to be part of how we figure out how to actually learn from data. So at this point, you might be thinking, hey, Professor Welch, you've been talking about how to not do machine learning for like 2 lectures. How does this thing actually work? And now is when we start to turn the corner a little bit, and you'll see this in the videos as well. But what I want to do is let's go a little bit further. I don't know if we'll make it all the way through here. We'll see. I might send you to the videos for some of this, but we're going to get into a little bit of math. And don't let the math scare you. It's in the video too, and I won't quiz you over the details of the exact mathematical implementations, but I'm really trying to just build some intuition. So what I want you to think about a little bit is how do humans learn, right? Maybe there's some ideas we can borrow from human learning. And I think we might leave it there for now. So I think next lecture we might pick up on, I think we'll pick up here. So I encourage you to watch more of the videos. We'll have one more lecture left in this series. We'll pick up around here, and we'll also get into decision trees. Decision trees are a really cool topic. You do not need to be a decision tree expert to do well in this course, but I do want you to have some exposure to them, and we'll talk about them in some more detail next class. Do watch the videos. I might go a little bit fast over this at the beginning of next class, and I might kind of hop right into decision trees because we have a lot to cover there. But the main thing, again, like I said here, is concepts. I really want you to come away with this with a better conceptual understanding of what machine learning is and how it works. So do get to work on your programming challenge. You don't have to know what a decision tree is to do well in your challenge. Really, it's to finish your challenge, there's gonna be some kind of heuristics and experimentation you'll have to do. So do get started on that. I will see you guys on Tuesday, and have a nice weekend. Thank you.